All right, so our third kind of reaction is called a redox reaction or an oxidation reduction reaction. So we've had precipitation, which is a coming together of ions to form a solid. We've had an acid-base reaction, which is a transfer of hydrogen ions. And now an oxidation reduction reaction involves the transfer of electrons from one species to another. Oxidation is defined as the loss of electrons, and reduction is defined as the gain of electrons. So sometimes you can remember with the mnemonic oil rig, oxidation is loss, reduction is gain. It seems a little weird that reduction is gaining, but keep in mind that electrons are negative, so you'll see why reduction is called reduction when we get to doing the numbers, because the number will actually come down because you're gaining a negative charge. Anyway, oxidation reduction always occurs spontaneous or simultaneously. You have to have both. You can't have one without the other. So here's some examples of oxidation. Sodium will lose an electron to become the sodium ion, or iron becomes the iron 3 ion, which loses 3 electrons. Chlorine can be reduced to the Cl negative. Oxygen can be reduced to O negative 2. Don't forget these are those diatomic elements that only exist in diatomic form. And then you can see down here, this is a combination. This is actually iron being rusted by oxygen. So the iron has actually lost electrons and the oxygen has gained electrons, and it formed rust. So we could look at a very simple oxidation reduction reaction. It's a reaction of an iron nail. If you put an iron nail into a solution of copper 2 sulfate, you'll see what happens. And let me just start out by saying that iron here, notice that iron doesn't have a charge, so it means the metal, iron metal in its elemental form. And then here, this is an aqueous solution, so actually it's copper ion and sulfate ion. So that's what's dissolved in solution. On the other side of this, what happens is we have iron sulfate, so iron and sulfate are in the products, and then copper now is the metal. So we'll see what happens in the next slide. Okay, so you can see here this is the copper sulfate solution is a blue color. Here's the iron nail, which is just solid iron metal. When you stick the nail in there, it's a spontaneous reaction, and what happens is the iron will start to lose electrons. As the iron loses electrons, they become iron ions and go out into solution. Meanwhile, the copper ions will gain the electrons, and then they get pulled and they deposit on the nail. And so you can see some of the iron is leaving and some of the copper is depositing. And so two things, you see that the solution has gotten a little bit lighter because some of the copper has disappeared from solution, and then the nail has gotten the rust on it, the copper, well, it's not rust, but it's copper deposited copper. So that's what's happening in a redox reaction. So the net ionic equation shows the true reaction. So like I said before, remember I had the copper sulfate and the iron sulfate. The sulfate is a spectator, so it cancels out. So the iron actually loses 2 electrons, so iron has been oxidized, and the copper has gained 2 electrons, and so it is reduction. So another way that you can figure out oxidation and reduction, if you can't see electrons leaving or coming, is to use oxidation number. So an oxidation number is a way of keeping track of electrons in a reaction. So the oxidation number, or sometimes also called the oxidation state of an atom, so if it's an atom in its elemental form and it's all by itself, it's going to be equal to the charge of the atom. So if it's an atom without a charge, it'll be 0. If it's an ion with a charge, so monoatomic, meaning it's the only element, then it'll be equal to that charge. But if we have a compound The oxidation number is a hypothetical charge assigned to an atom in a substance, and we have to use simple rules. So let's go through the rules real quickly. The first rule is that, like I just said, elements in their elemental form that have no charge will always be zero. Don't forget that includes things like oxygen. Remember, oxygen is diatomic, so it's still only oxygen in that compound. So it's an elemental oxygen, and it's zero. Nitrogen, hydrogen, anything all by itself with no charge will be zero. It could be carbon, it could be copper, metal, so like we saw, iron, metal, anything. Now, if it's an ion, then it's equal to its charge. So like we saw the copper 2+ ion has an oxidation number of 2, +2. The iron also had a +2. Oops, well, iron can be +3. The iron we saw in that last example was a +2. They're both possible. So loss of 3 electrons, loss of 2 electrons. Do keep in mind that a lot of times you'll see group 1A and 2A metals in a compound, and you can automatically assume that the group 1A is +1 and group 2A is +2. Like anything with sodium is, if it's in a compound, it's always +1. It's its only possibility. Now oxygen, now we're starting to talk about compounds. So if an oxygen is in a compound, it's almost always -2. Now there is an exception where oxygen can be a peroxide and it's actually a -1. But I'll tell you that if that happens, most likely it is it'll break another rule. So you can pretty much assume oxygen in a compound is a -2. If it breaks a rule, then it's probably a -1, and I'm going to show you an example, but most likely I won't give you one of those. I would say I won't. So you can assume it's -2 in almost all compounds. Hydrogen, similarly, has only one of 2 possibilities. It's almost always a +1 in compounds. However, if it's paired with a metal, then it's a -1. So that's, and you know what a metal is and a nonmetal. So if hydrogen, oftentimes if it's paired with a metal, the hydrogen's written second. Whereas if it's written first, it's generally with a nonmetal. So +1 here, -1 here. In any compound that fluorine is in, it'll be a -1. A lot of the other halogens, so chlorine, bromine, they tend to be -1. However, they can be other things, chlorine, bromine, iodine, they can change. And so you can't assume they're -1 unless pretty much the only examples I give you is if that if it's not -1, you'll know the rules for everything else and be able to find out what the halogen is. But if you don't know everything else, then you can just assume it's -1. Finally, what we have to do is look and see that compounds and ions are their oxidation number equals their charge. So if you've got a neutral compound, the sum of all the oxidation numbers will equal 0. If you've got a polyatomic ion, then the sum of all the oxidation numbers will equal the charge of the ion. So I'm going to show you some examples in just a minute, and I think you'll see what I'm talking about. All right, so let's find the oxidation state for sulfur in the following compounds. H2S. So we do have a rule about hydrogen. Hydrogen in compounds is almost always a +1. So, and we know that the total has to equal 0 because the charge on H2S is 0. There's 2 hydrogen and they're each a +1. So sulfur has to be whatever makes this total 0. So that means sulfur has to be a -2. I don't want you to get too confused. A lot of people, we spend so much time on ions and charges of ions, and we know how to predict ions from the periodic table. But I want you to keep in mind that oxidation numbers sometimes parallel charges, but sometimes they're very different. So don't just assume they're the charges that you already know. These can vary, especially nonmetals can vary a whole lot. And so they sometimes look like they might be what we expect, but then they can be something totally different. Okay, so S8 Well, it's just an element. It's only the element by itself. There's nothing else, so it has to equal the charge if it's an ion, or just it has to equal 0 in this case because the total is 0. So each S has to be a 0 for that to be 0, so it's a 0. Okay, in SCl2, now Cl is a -1 in many compounds. Since we're trying to find the S, we have to assume Cl is a -1, otherwise you would be told something different. So S is a Cl is a -1, so S plus 2 times a -1 has to equal 0, which means this time S is a +2. So you can see it varies quite a bit. In this case, we actually have 3 elements, so hopefully we have enough rules. But like I said, sodium in any compound will be a +1, and there's 2 of them. Whatever S is, that's what we're trying to find out. And there's 3 oxygens, and each oxygen will be a -2. It'll be a -2 unless it breaks some other rules, so you can just assume -2. So that means I've got 2 plus S minus 6 equals 0. So that means S is a +4. Finally, don't forget that if you have a polyatomic ion and there's a charge involved, the total has to equal the charge, not 0 anymore. 0 is what the charge is, so it can equal 0, but in this case it has to equal -2. So sulfur plus 4 oxygen, each oxygen's a -2, has to equal -2, so that's S minus 8 equals -2, and S equals +6. So that's how you find oxidation numbers. Usually you'll be able to tell what at least all but one are. I've got a few other examples on the next page. Oh, and I'm going to go through, hopefully you can see that through the writing, but again, this is just what I went through. So 0 here, S is all alone. Here it's a +2 because each Cl is a -1. Here S is a +4 since Na is always a +1 and O is almost always -2. And then finally S is +6 here. So it can range quite a bit. So let's do a few more, some other oxidation number examples. There's no rule for phosphorus, so we're going to have to figure out what phosphorus is. And then oxygen, almost always -2. So now this time there's actually 2 phosphorus. There's 5 oxygen. Each of those is a -2. And there's no charge on this molecule, so it has to equal 0. So 2 phosphoruses minus 10 equals 0. So 2 phosphoruses equal, I know you could probably do that faster in your head, but I'm just wanting to work through. So each phosphorus is a +5. Let me write this one down here so I don't block the, the printing. Now here, this is one of those cases we actually have a rule for both of these. H with a metal is always -1. Na being in the first column is always a +1, so that was pretty easy. And you can see the total has to equal 0. Now this is one of those examples where the oxygen is actually not a -2. And the reason we can know that is because barium has a rule. Barium's in the second column. It's a +2. So +2 plus whatever oxygen is has to equal 0. That's why I put the line there so you can tell between oxygen and 0. So barium, so each oxygen, 2 oxygen is going to equal -2, so each oxygen is going to equal -1. So this is a peroxide, barium peroxide. That's a really special case. So like I said, I'm not going to give you that unless I kind of give you a little heads up. So almost always oxygen will be a -2, unless you know the other one and it breaks that rule. Okay, so finally we have this last one, and again, the total is -2. Each chromium, we don't know what that is. There's 7 oxygen, and they're each a -2, and the total has to be -2. So we've got 2 chromiums minus 14 equals -2, so 2 chromiums equals 12. So each chromium is +6. We do generally, even if it's positive. I mean, I wouldn't count it wrong, but generally we put, for oxidation numbers, we generally put if they're positive or negative. So again, I've kind of gone over my thing here, but this is just what I just went over. And so that's some examples. Now, another way of describing a redox reaction is one where one or more element involved undergoes a change in oxidation number. So this is kind of what's very helpful to remember, especially if you're good at finding oxidation numbers. You can see how they change during the reaction. So you can see here, iron has an oxidation of 0. Copper has an oxidation number of +2. Here iron is a +2, and here copper is a 0. So the iron has gone from 0 to +2. So oxidation is an increase in oxidation number. So iron is what's being oxidized, and we already knew that because it's losing 2 electrons, but it's just another way of looking at it. And this is a simple one, but sometimes it's not as easy to see, and so this helps if you can find oxidation numbers and see how they're changing. And you can see here reduction is a decrease in oxidation number, so the copper is going from +2 to 0, so it's a decrease in oxidation number, or in other words, a reduction. So when the number goes down, it's a reduction. We can also write this reaction in terms of 2 half reactions where we show the electron. So here, the iron, here's the oxidation half reaction. Iron is actually losing 2 electrons. And then here, copper is gaining 2 electrons. So that's the reduction half reaction. We can actually, if we want to, we can draw a line under there. We can cross off the electrons then, and we go back to getting our original reaction without. So these are the 2 half reactions. And we'll see why this is important in just a minute. So like I said, so one more thing, because we like to make things difficult. If something is reduced, it's actually allowing something else to be oxidized, and so it's an oxidizing agent. So whatever is reduced is an oxidizing agent, and whatever is oxidized is a reducing agent. And so we often say something is oxidation, and it comes from oxygen. Oxygen is often the thing that's being reduced, and it actually allows something else to be oxidized. So that, I think that's where originally the terms came from. So in this case, because the iron has been oxidized, it is the reducing agent. And because copper has been reduced, has gained electrons, it is the oxidizing agent. So just keep that in mind. If you see the word agent, it's the opposite. Okay, so this is why it can be helpful to do those half reactions. So at first glance, this looks like it's balanced. We've got zinc, 1 zinc on each side, 1 silver on each side. But notice that charges are not balanced. On the left-hand side, we have a 0 and a +1. On the right-hand side, we have a +2 and a 0. So this equation is not balanced because the charges don't appear. And if we had our counter, like our negative ion, the number of negative ions would not be balanced because the charges are not balanced. So the best way to balance a simple redox reaction is to break them back up into their half reactions. So these have a mass balance, but not a charge balance. So if we pull them apart, we can see again that zinc has gone to zinc +2, means it had to have lost 2 electrons, where silver +1 to 0 means it only gained 1 electron. So now you can clearly see that they have to have the same number of electrons in order for the reaction to work. So what you can do then is just get the electrons to match by multiplying one or the other or both equations. Okay, so in this case, what we have to do is double this equation. So if we double the 2 electrons, they'll cancel, which means we have to double the silver, silver 0 and the silver ion. So when we add them back together, then you can see again, now this time the 2 electrons cancel, and now we have both the mass charge, a zinc on either side, 2 silvers on either side, and then a charge balance because you've got a +2 on the right and a +2 on the left. So this is now a balanced redox reaction. The textbook actually goes more into some other balancing redox reactions, which we're not going to go into it right now. So this would be the most that you'll have to do is just these easy half reactions. All right, so we talked about we can classify reactions as precipitate, acid base, or redox. There's actually another way that we can classify reactions, and that's sort of by their mechanism, how they go about the reaction. And so there's actually 4 general types of reaction. There's a combination reaction, decomposition reactions, displacement reactions, and under displacement, we have single or double displacement. Sometimes they're actually called, I'm going to write it here, sometimes they're also called replacement. So displacement or replacement are the same thing. So we could either have a single displacement or a double displacement. And then combustion is kind of gets its own little category. So this is a combination reaction. A combination reaction is just a reaction in which 2 substances combine to make a third. So when you only have one product, you can assume it is a combination reaction. 2 things combine to make one. This happens to be sodium plus chlorine given as sodium chloride. Now, combination reactions can be redox. This happens to be a redox, and let's just look at it. Sodium here has a 0 charge. Chlorine has a 0 charge. Here, chloride has a -1 charge and sodium has a +1. So sodium is being oxidized and chlorine is being reduced in this case. So this is a redox. And this is what it looks like. Sodium, if you put a little piece of sodium in there and there's chlorine gas in there, and then you can get it a little bit of a spark to get it going, and it'll be a very exothermic, very releasing heat, and it turns into salt. Another combination reaction that is not redox, here's another example. So this would be combination because CaO plus SO2 gives us CaSO3. And let's see, I can do it really quickly. O here has an oxidation of -2. Ca has an oxidation of +2. O here is a -2, so that means S has to be a +4. And then if we look at this, calcium again has to be a +2 because it's in the second column. Oh, this will be -3 times -2 is -6, so this again has to be 4. So you can tell if it's redox or not by looking at the oxidation numbers. They don't change at all, so this is not redox. Decomposition then is just the opposite. Decomposition is a reaction in which a single compound reacts to give 2 or more substances. All right, so here we have one reactant and it's breaking down into 2 or more products. This is the decomposition of mercury oxide. It's a redox reaction. I can go through again. Oxygen in compounds is a -2. Mercury will be a +2. Here, because it's an element, it's 0. Here, because it's an element, it's 0. So mercury is being reduced and oxygen is being oxidized, which is kind of unusual, but happens. Here's another example of a different decomposition reaction that is non-redox. This is when calcium carbonate, limestone, actually will decompose into calcium oxide, which is quicklime, and CO2 escapes. Mainly, I just want you to identify the type of reaction. Is it decomposition or combination? I'm just showing you that they can be redox. So they kind of fall into, there's redox, precipitation, acid base, and then we have our different types of reaction, and you can have any of those within each one. Okay, this is the mercury the mercury oxide breaking down into mercury and oxygen. This is the mercury oxide, which is orange, and then there you could see the mercury and then bubbles of oxygen. Okay, displacement reactions. Like I said, you can have either a single displacement, but a displacement reaction is one thing replaces another or displaces another. So a single replacement or single displacement reaction is a reaction in which an element reacts with a compound and the element gets displaced. So you can see here, zinc is all by itself. Here you have hydrogen and chlorine together. Now the zinc has replaced the H and become zinc chloride. So the zinc is now paired up with the chlorine and now H is by itself. So an element replaces another element in a compound and then the element is by itself. So this is a single replacement or single displacement. Single displacements are always redox reactions. And if we go through real quickly, zinc is a 0, H is a +1, Cl is a -1. Here, zinc is a +2 because Cl is a -1, and hydrogen being in its elemental form is 0. So zinc has been oxidized and H has been reduced. This is a reaction we do in lab. So they're always redox. This is, so that's zinc reacting with hydrochloric acid. The zinc metal becomes zinc ion, and the chlorine ion is just the spectator, and then the water, the H on the water will become hydrogen gas. A double replacement or double displacement reaction is a reaction where two elements replace each other. So that's the difference. Notice in that last one, zinc was by itself and hydrogen was by itself. Now in a double displacement, you've got, like here, calcium with hydroxide, you've got sodium with carbonate, and then the calcium and the sodium have changed places with other compounds. So now we've got the calcium with the carbonate and the sodium with the hydroxide. So there's 4 things and 2 replace each other. So that's double replacement. And double replacement are never redox. They're either precipitation or acid-base reactions. The last category, which kind of gets its own little category, is called combustion reaction. And a combustion reaction is just a reaction where a substance reacts with oxygen, usually with the rapid release of heat to produce a flame, but not always. So here is actually combustion of iron. Iron reacts with oxygen to give us iron oxide. And actually, if you took like some iron wool and lit it on fire, it would flame up. So it would rapidly release heat. But you can also have like your iron patio furniture reacting with oxygen, and that probably wouldn't burst into flames, but it's still going to give off heat, just much slower. This is a redox reaction. So that's a combustion reaction of iron wool. Combustion reactions are redox reactions. Here's another combustion reaction that we're very familiar with. This would be methane, natural gas, reacting with oxygen to form carbon dioxide and water. So this is also combustion. And like I said, combustion are redox here. Iron's going from 0 to +2, +3, and oxygen's going from 0 to -2, so oxygen's being reduced. Here, carbon is a it's a -4. Carbon is a -4 because hydrogen is a +1. Here, elemental, oxygen is 0. When carbon's attached to oxygen, it's a +4. And the hydrogen is still +1, and now the oxygen, oops, let's see. Yeah, no. Yeah, the hydrogen's +1, the oxygen's -2. So notice that the oxygen has gone from 0 to -2 in either case. So that's reduction, and the carbon has gone from -4 to +4, so that's oxidation. So that's the steel wool burning, and you can imagine what methane burning looks like. So the 3 major types of reaction: precipitation, switching and coming together of ions to form a solid that is not soluble in water. Then there's the acid-base reaction, where there's a transfer of an H+ ion from an acid to a base. And then there's an oxidation reduction reaction, which is the transfer of an electron from one species, which is the one being oxidized, to another one, the one being reduced. So those are our three major types of reactions. And then we have our four types of mechanisms: combination, decomposition, displacement, single or double, and then combustion.